Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on 2D and 3D integration, and we already discussed about 2D integration. Now let's look at the 3D integration. All right. And the goal here is that, okay, 3D integration, we want to reduce the problem of a 3D integration in its most general form into three one-dimensional integration, because we already know how to accurately calculate one-dimensional integration. Okay, and again, one of the variables is always can be considered as the free running variable. In this case, we have x, y, z, and we're fixing the boundaries of x from a to b. So x is our free running variable, which by convention I call it variable number 1. So in my convention, the variable 1 is always defined as the free runner. All right, both in the function, integral function, and in the domain object. And the second and third variables can be a dependent variable. All right, so those can be dependent variables, and what we know is that my convention is that the second variable var2 only depends on the first variable var1, and var3, the third variable, could in fact depend on both var2 and var1. All right, so this is my convention. var1 is free runner, var2 only depends on var1, and var3 only depends on var1 and var2. All right, so this is the most general case. It cannot get any more general than this, right? We have a f of x, y, z, and they could be connected, so this function may not be separable in terms of the x, y, z variables, and the domains are also connecting the variables together. Now we have to convert this into 3 steps, and in each step we want to perform a one-dimensional integration, right? So obviously our function, the three-dimensional function, is a three-dimensional integral function, and then we have a three-dimensional domain. These two are interfaces, and then we have a integral 3D object that takes these two, breaks them into 1D integration, right? So the first thing is that we need to integrate always on var3, because var3, the domain, could depend on x and y, and this should return a two-dimensional function, j of x and y. And then we pass this to, and then we do another integration on var2, because the domain of var2, the boundaries could depend on var1. Okay, and then this returns a one-dimensional function with a fixed boundary, only depends on var1, and then we finally calculate this and get a numerical value for our integral. Okay, and again, this approach of having var1, var2 depending on var1, and var3, the domain of var3 depending on var1 and var2, gives you a very general case in which you can choose any coordinate system to do the integration, right? It doesn't have to be Cartesian. It could be cylindrical, spherical, or any other coordinate system. So let's head to Eclipse and try to implement this. So we already have this integral project, and we have integral 2D, and we have interface for integral domain 2D. Let's copy these. Interface for integral 3D, we already have implemented this. Function 2D takes two variables, var1, var2. Integral function 3D takes 3 variables, var1, var2, and var3. And again, remember our convention. var1 is free runner, so this is my convention. My convention is that var1 is free runner with fixed boundaries. var2 only depends on var1, and var3, the boundaries of var3 depend on both var1 and var2. Okay, and we have integral 1D, integral 2D. Let's do integral 3D. Integral 3D. All right, now in the integral 3D, we're going to have a integral function 3D func, and then we're going to have integral domain 3D. All right, and then we're going to have a constructor public integral 3D, and here we're going to pass in a function, integral 3D function, and domain 3D object, right? That defines the domain. And then we have to use this keyword to make sure no shadowing happens of the variables. Domain 3D equals domain 3D. All right. So this is the here, and then we're going to have one method, public double. Let's implement Gauss-Lagrange. And in the Gauss-Lagrange, again, I'm going to use a 5-point Gauss-Lagrange. We can do 10 points, doesn't matter. And then in the Gauss-Lagrange, what we are going to do is, so eventually what we are going to do is we're going to have an integral 1D. So this is the last step. Basically, we're going to write it backward. In the last step, or step 3, which was the integration of qx, right? So in the integration of qx, we're going to have an integral 1D. So integral, let's call it q, function q, and the new integral 1D, and we're going to pass find q, right? Let's go back here. We're going to, yes, so we're going to pass a function find q, and then we're going to double result. The result is going to be the result of integrating this over, let's call this Gauss-Lagrange, and the boundary over its boundary, and then we're going to return the result. And what are the boundaries? The boundaries are from the free runner, right? So the last step is integrating over free runner variable, which by our convention is var1. So we have to get call the domain 3D, get var1 mean, and then domain 3D get var1 max. All right. So mean and max of var1. Now we have to create this find q. Now in order to find q, we go one step back. This is step 2, and step 2, this is basically integrating over var2, right? And it returns should returns a function. It returns a function of var1. So what we have to do here, we're going to make sure that we have an integral function 1D find q, which is equal to var1. It should be a variable of var1, and we're going to use a lambda expression. And in order to do the lambda expression, we know that this find q, this q function is a result of 1D integration over var2, right? So we're going to have here, we're going to have new integral 1D find j, and then Gauss-Lagrange start and end. All right. And this j function, find j, again, we're integrating over var2, so we have to call our domain 3D and get var2 mean, and we pass in var1 because var2, the domains or the boundaries of var2 might in fact depend on var1. So domain 3D get var2 max var1. All right. And so okay, so var2 mean, var2 max, var1. All right, now we're going to go, so this was step 2, and one step back, we need to define this find j. And again, this j is the result of the integration over the original function, all right, over the third variable, var3. So we have to go to actually step 1, integrating over var3, and returns a function of var1 and var2. All right. So what we are going to do, we are going to say that integral function 1D func j equals to So here we're going to say that, okay, var1 goes to we could in fact find j. I think we should do a nested so instead of this we should do a nested object. So we have to create this func q, right? And then we know that integral function 1d func q equals var1 to something, right? And that something comes from a new integral 1d of some function func basically we can do this, or we can so another way, instead of having this, q is the result of a double integration, so we can do a double integration. That's one way. So let's try that. So we're going to say, okay, integral function 1d comes from the fact that var1 it's going to be a function of var1 and it's going to be a function of var1, all right? And it maps var1 to new integral 2d, right? And in the integral 2d that makes it look complicated. So let's try just nested integral 1d of some function func j with the let's say Gauss Legendre, and we're going to integrate over basically var2, right? So domain 3D get var2 mean, domain 3D get var2 max, okay? And let's put the semicolon here. So what we are doing here is but then the question is this func j, how do we implement this func j? Because this func j is supposed to be depending on var1 and var2, right? So what we are going to do, we're going to use another lambda expression inside here. So here we're going to say that this function maps var2 basically to something, to the result of an integration. So new integral 1d of some function which was our func 3d func value var1 var2 var3, right? Let's see again. So we want to calculate this. So we need to first find qx, and qx is the result of integrating over var2, okay, over func j, integrating. Yes, so here we're defining func j, and func j is basically the result of integrating our function over var3, okay? So here what we're saying here is that, okay, var2 maps to here, integral function, and this function requires map3 func dot value var1 var2 var3, and the construct is ambiguous. So I guess here in this integral 1d, let's first comment this out. Guess here we also get some problem, but let's also comment this out. All right, so we don't have the ambiguity anymore. So let's see what we're trying to do here. We're trying to do some nested integration. All right, and var1, so func q is a function of var1. So we're mapping var1 to the function. That function is the result of integrating one-dimensional integration over var2. Okay, but the second function also depends on result of integrating over var3, which is the original function. So what we do here, we call the Gauss-Legendre. Let's just see. So we are integrating over var2, and now we are integrating over var3. Gauss-Legendre, and we want to do the okay, so let's add the start domain 3D dot get var3 mean, and then domain 3D get var3 max, var1 var2 var1 var2. So it's just a little bit of nested code, nested integration. Okay, so what we are doing here is that we're mapping var1 to the function for function q, and that one is the result of integration over var2, and that function also is the result of integration over var3 from the original three-dimensional function. So we integrate over basically we integrate over original 3D function, okay, on the domain of var3 mean var3 max, and it returns this basically becomes a function, a value that depends on var1 and var2, and then we integrate over var2, okay, on the domain of integration, basically domain var2 mean var2 max. All right, and then it becomes a function of var1, and then we again integrate it over var1, and this should work. So let's go ahead and try to test it. Integral 3D test integral new class test integral 3D. Okay, and let's have a main method here, and in the main method I'm going to have some method called test1, and let's just generate it. In test1 I'm going to get the volume of a sphere, and in order to do that I'm going to use a spherical coordinate system. The reason is that when I choose spherical coordinates, dv is dx, dy, dz, right? But then the problem is that the boundaries are kind of complicated. So if I use Cartesian dx, dy, dz, then my function is very simple. F of x, y, z is 1, but domain is complicated. Okay, so in the spherical coordinate, dv is r squared sine of theta dr d theta d phi. Okay, so my function is still function of r, theta, and phi is r squared sine of theta. It's not complicated, but the good thing here is domain is very simple. Domain is simple because what happens is that in spherical coordinate, in order to cover the whole sphere, r goes from 0 to the radius, and theta goes from 0 to pi independent of r, and phi goes from 0 to 2 pi independent of r and theta. So all the domains are independent. And that's the whole point of changing coordinate systems, because we always, not typically, always want to work with a coordinate system that makes the domain very simple and, if possible, independent for different variables. That's always the choice, because that shows the symmetry of the problem. So let's do a spherical coordinate system. So what I'm going to do is that I'm going to define an integral function 3D func, which is mapping var1, var2, and var3. And again, because in the spherical coordinate the domains are independent, it doesn't matter which one is the free runner. Okay, so let's assume that radius is the free runner, and then theta is var2 and phi is var3. But remember, our convention is that var1 is free runner always, var2 is only depending on var1, and var3 only depending on var1 and var2. So here my function becomes radius times math dot sine of theta. Okay, so this is my function, and now the domain, integral domain 3D, new integral new integral domain 3D. So let's just use an anonymous class, and in the anonymous class let's start with var1. So var1 is radius, and let's also define our exact value, because this is the problem that we already know the solution. So double radius value is, let's say, 5, and then double exact is 4/3 times math.pi times radius. Let's just use the power function, math.power radius val to the 3, and sys out exact equals exact. All right, so that's the exact value. So var1 is radius, it goes from 0 to radius val. Okay, var2 is theta, it's independent of the domain, is independent, it goes from 0 to pi. And var3 is basically is phi, and again its domain is independent. In this case, in the spherical coordinates, it goes from 0 to 2 pi. All right, now we have our integral function and domain of the integration in spherical coordinates. We need to create our integral 3D integral finder, or integral spherical equals new integral 3D func domain 3D, and double result spherical equals integral spherical Gauss-Legendre, and sys out result spherical equals plus result spherical. All right, so let's test it. And as you can see, the integration took quite some time, but it returns the exact result, right? 523.598 7755 98299. All right, so Gauss-Legendre worked, but it was pretty slow. As you can see, I'm running it again, and it's thinking and thinking and thinking. Yes, and the reason is that so we're doing this nested integration, and what we're calling is Gauss-Legendre method, and in the Gauss-Legendre we're using 100 subintervals. It might not be the best case. Maybe we probably don't need 100 points, 100 subintervals, and that's what's limiting the performance, right? And then the question is, let's try to do, for example, Simpson. So instead of Gauss-Login, I can implement this for integral 3D with a different method. Let's say Simpson, all right? And again, the code is exactly the same. Ctrl-Shift-F to format it. And the only difference here, instead of Gauss-Login, I just call Simpson method start end. All right, and in the Simpson we need to also specify how many sub intervals. Let's say we only say 100, let's say 50, or let's keep 100. But Simpson is probably faster than the Gauss-Login. Simpson, and then we're going to have 100, and instead of Gauss-Login, Simpson, and then we're going to have 100 again. All right, so in the test here, instead of having Gauss-Login, I'm going to call the Simpson method. Simpson. Okay, now the Simpson is pretty faster than the Gauss-Login, but it still gives a pretty accurate result. 577. So we have 598, 7, 7, 5. So it has about 60 decimal places of accuracy. All right. So this was the 3D case, and now we can do basically some advanced vector calculus using this kind of integration. Okay. Now what happens if we decrease the number of terms here? For Simpson, let's say 50, and then still fast, but we're losing some accuracy here. Okay, and again, this accuracy, we still have like 5 decimal places of accuracy, which is good enough. Okay, and if I wanted to do this calculation basically in Cartesian coordinates, it was kind of difficult. But let's try to do this in cylindrical coordinates. And for cylindrical coordinates, things are also not that easy, because the boundaries, again, the problem here is calculating the volume of a sphere, and because of the spherical symmetry of the problem, it's always recommended to use a spherical coordinate system. Okay, now you can try to find the volume of the cylinder, and in that you will find that, okay, because of the cylindrical symmetry of the structure, we should use a cylindrical coordinate system. All right, thank you for watching. I hope you enjoyed this, and I'll see you in the next video.